So can you share your slide, Prof?
Yes. I think I will share my screen better because I will do the origin demo a little bit.
Okay.
I'll share my whole screen.
Yes, we can see.
Yes, good.
So, okay, may I start, Prof?
Yes, please go ahead. Yes.
Good morning, everyone, and welcome to our another special lecture session. Today we have our very famous Professor Chia from Material Science Department and at University Kebangsaan Malaysia. So I would like to invite him for our today's session. Today he will discuss about Raman and Fourier FTIR. So please help me to welcome our today's facilitator, Professor Dr. Chia.
Okay, thank you very much. Thank you for the kind introduction. So today I will give another lecture specific on FTIR, Fourier transform infrared spectroscopy. So Raman, I will give it this topic in coming lectures. So basically, these two instruments are complement with one another. So if you talk about vibration spectroscopy, you cannot escape from Raman and FTIR, and they are both share the same importance purpose in terms of characterizations of materials. So I'm Chia, so from Material Science Program, University Kebangsaan Malaysia, also known as UKM. So a little bit of my background. So just to let you know where I come from. So what I did previously. So my research area mainly focus on nanomaterial synthesis. So main interest is on structure control, so that we can tailor the characteristics and also properties of the materials. And this material can be potentially used in various applications such as wastewater treatment, supercapacitor, and also hydrogen productions, and also catalysts. So those materials that I'm interested in, for example, metallic nanostructures, magnetic nanoparticle, so graphene oxide, and also nanocellulose. So a little bit of overview. Just share a little bit some of the important pictures that you have some idea what we are doing in UKM, what we have done previously also. So basically all are nanostructures materials. So done by my master and PhD student. And also some nanocomposite material. This is meant for final applications. Example, aerogel, hydrogel, rubber products, and also some catalyst substrate for different types of chemical reactions. So these are our work in UKM. So let's start to talk about FTIR. So as I told you just now, FTIR spectroscopy is a vibration spectroscopy. So it actually explains or extract information about molecular vibrations. And we know that different types of chemical compound will have different frequency in terms of the vibrations. So this is a sort of fingerprint of different or all types of chemical compound. So FTIR is an analytical technique, okay, very popular one, very versatile, widely used in research in industry as well. So to identify also and also to study chemical compositions of materials. And don't forget also FTIR can also do online measurements of chemical productions in the industry. So it's offline and online instruments. So the basic principles of FTIR basically we always talk about chemical bonds, okay, and different chemical bonds will absorb different infrared radiations in terms of different frequencies. Okay, so at specific wavelength. So specific wavelength means a specific frequency. Okay, so by knowing the frequency or the wavelength of from the signal, then you can estimate or you can identify types of chemical bonds. So from the chemical bonds, you can try to correlate with the compound that you are interested in. So in FTIR, basically we measure the IR absorptions after the IR photon, okay, the IR photon passing your sample. Then you measure the IR and you subtract with the incoming IR. Then you know what is the frequency or wavelength that disappeared. So from the signal, okay, you identify what are the wavelength that disappeared. Then you know that this is the wavelength that is absorbed by your sample. Okay, then we fit with library database. Okay, then we can know what kind of chemical bonds appear in your sample. Okay, so not only identify actually, but you can also know the concentration. Okay, you can kind of estimate the concentration of that particular chemical bonds in your sample. Okay, so the absorption of IR by your sample is basically due to the vibration and also rotation of the molecule. So I'll explain detail later. So the whole idea of FTIR basically is you have a IR source, okay, IR source with a certain wave frequency or wavelength. Then it will passing your sample. If your sample is IR sensitive, it will absorb certain wavelength of IR. Then whatever detected are those wavelength that not absorbed by your sample. So from there we can we know what kind of chemical bonds are in your sample. Okay, so what is IR? IR is infrared. Okay, infrared is basically electromagnetic wave or electromagnetic radiations, or we can call it light. And why we feel sunlight hot, mainly because of IR wave. Okay, so we feel hot because of IR. So it's a longer wavelength compared to UV. Okay, compared to X-ray. I give a talk last week about XRD. So XRD, the wavelength is much shorter, okay, and the frequency is much higher. So the energy of X-ray is much higher compared to IR. So the IR radiation will penetrate your sample, okay, you passing through your sample. So either solid, liquid, or gas, okay, not only solid liquid, but also gas. So then the IR wave will interact with the molecular vibrations. So why there is interactions? Mainly because of the wavelength and also the frequency are the same, in the same range of frequency. So you have absorption will, the absorption will happen. So there are three different regions of IR. So near, mid, and far IR, and different instruments will serve different purposes, because you have far IR spectrometer, mid IR spectrometer, and also near IR spectrometer. The differences are made. One of the major differences is the IR source. So the most widely used FTIR is mid IR, okay, because it covers a wide range of molecular vibrations regions that are mainly on organic, carbon and hydrogen, carbon and oxygens. So these are most sample that we are dealing with. Okay, but some people actually have interest in terms of near IR and also far IR, but it's out of our topic today. Okay, so the frequency of the absorbed IR radiation actually correspond to the nature frequency of the molecular vibrations. So the chemical structures you have, functional group that you have, this functional group vibrates at certain frequency. If the frequency is consistent with the IR radiation frequency or the wavelength, then it will absorb. Okay, so this table shows different frequency, okay, for different types of chemical bonds. So from there, you can kind of actually identify whether this is fall under this functional group or not. But bear in mind, normally IR spectrum is not as what you imagine. It was always quite complicated, and also a lot of overlapping. and that require a lot of fine tuning in terms of during measurement, as well as data interpretations. So how you collect the data, okay, how you carry out the analysis. And most of the time, I'm not sure whether what is the practice in PSU. Some university actually students send sample, okay, to the technicians or the operator to run the instruments, and the operator will actually will only run one time, then just one scan, then he or she will send you the result. This shouldn't be the way. The right practice should be repeat and repeat until you get the best signal you have. Okay, so and FTIR spectrum normally is a repeat of I think quite messy. Okay, a lot of noise in terms of a lot of overlapping in terms of the absorbance peak and peak. So I will explain later how to do baseline corrections, and also how to do smoothing of the spectrum. Okay, so this is basically I think I use the same picture in XRD, in my XRD lecture. So here is X-ray. So you see the frequency is much higher. Okay, wavelength is shorter, much shorter. So compared to IR, IR is for within here. Okay, you have near IR, mid IR, and far IR. So mid IR FTIR is basically covered this range. Okay, so UVs is here. Okay, UV and visible is here. So if you know about X-ray, UV, and visible, then infrared, basically you can extract quite a lot of information from the sample, from atomic scale to the band gap, okay, electronic properties of your specimen, and also molecular vibrations, or the molecular vibration of molecular band of your sample. So these three are very important instruments, especially for material characterizations. Okay, so I will explain later what is wave number, what is wavelength. So just bear in mind, the shorter the frequency, the shorter the wavelength, the higher the frequency, and the greater the energy. Okay, so FTIR is non-destructive test. So the sample will be safer, okay, after the testing. Okay, so IR, mid IR, near IR, and also far IR. So they have different wavelength. So far IR is longer in terms of the wavelength. So mid IR in the middle, near IR is much shorter. Okay, so normally in FTIR plotting, the x-axis will be in the unit of 1/centimeter. Okay, 1/centimeter. So there are reasons of it. Number one, more convenience. Okay, in terms of you just change it from wavelength to wave number. And also wave number is directly proportional to frequency. Okay, so if you have the frequency, then you can you know that the higher the frequency, the higher the energy. So you know this particular band, absorbent band, this functional group absorb higher energy compared to another band. So one reason, another reason, this is very important reason why the x-axis is in wave number, because of this. So we know that the higher the wave number, the greater the energy of that particular wavelength, okay, that particular functional group. Okay, then, and if you try to imagine, if you use frequency, okay, as the plotting, and the value could be very, very high, okay, very high, and very difficult for you to do comparison between different band and different functional group and different functional group. Okay, so, and another reason is because if you plot in wave number, then most of the time it will be directly proportional. Okay, it will be linearly proportional to the y-axis, which is the transmitted or absorbent intensity. Okay, so what is wave number? Wave number actually is a 1/wavelength. Okay, the wavelength is in centimeter. Normally wavelength is in a micron, okay, micrometer, but you convert it into centimeter, then you take this value 1/, this value, then it will be wave number. Okay, so this is wave number. Okay, one wave number, one complete oscillation is one wave number. So 3 microns means one wave number. This wave is, the wavelength is 3 micron. Okay, 3 micron. So what does it mean? So wave number of 3,333 means in 1 centimeter scale, there are 3,333 waves, okay, in 1 centimeter. So that is the meaning of wave number. So instead of you use 3 to 5 micron as a plotting of your FTIR. You try to imagine if you plot your FTIR spectrum, the scale maximum scale, the maximum wave number is 50, the minimum wave number is 3. Then very hard, very difficult for you to, the resolution is too small for you to really make comparisons. So this is a very, I think it's quite an intelligent way of converting the signal into wave number so that it is more detailed for you to make comparisons. Okay, so this is one, I think for many reasons. Not only this, I came across this one explanation, which whereby the reason why signal in 1 centimeter is because of historical reasons. Okay, historical reason. So, but consequently, these are also the benefit that we enjoy if you convert wavelength into wave number. Okay, so a little bit of theory, not in depth, but just want to catch your attention so that you have more idea about basic principle behind the FTIR. So molecular vibrations, you have molecule, then molecule actually constructed from different atoms, more than one atoms, only 2, 3, 4, 5, this depends. So and this frequency, okay, the vibration of the molecule, the frequency is related to the chemical bond. Different chemical bonds will have different frequency. So this is something that we have to accept it. Okay. Then this bond, actually, okay, this bond is actually a result of electrostatic attraction, also repulsion between atom and atom. So different type of atom, different radius, okay, with different charges, okay, different number of electron, different charge of the nucleus, that determine the strength, okay, the strength of the bond. So different strength of bond determine the frequency of the vibrations. Okay, so that's why FTIR used the concept of different chemical bond, different frequency. That's the fingerprint of the particular chemical bond. Okay, the strength and also nature. Okay, the strength of the bond and also nature of the bond determined by the frequency of the bond. Okay, so different types of chemical bond, different vibration frequency. So this is the assumptions that we made for FTIR. Okay, so for molecular vibrations, you have to imagine bond in between two atoms is something like you have a spring in the middle, okay, binding together. So this spring is elastic. Okay, it can be vibrating, it can be bending, it can be stretching between these two atoms. So for example, rocking. So you have one atom or one yellow atom and two blue atom. So they are rocking. Then they're wedging. They can even twisting. Okay. Sorry, they can stretch. Sorry, this is my mistake. This should be stretching. Okay, symmetry stretching. Anti-symmetry stretching, so means it's not really at the same rhythm. Then seasoning, then rocking, wagging, and twisting. All this motion will create different types of frequency of chemical bond. So means that one functional group, one chemical functional group, or one chemical bond could have more than one absorption band in FTIR. Because the same atom, okay, the same molecule with same atom, they have different vibrations in the molecular level. Okay, so by using Hooke's law, okay, Hooke's law, you can actually estimate the frequency for different types of chemical bond. Okay, these are the formula. So from force constants, you use force constant and the reduced mass and also velocity of light. then the frequency can be determined. Okay, but as a student, when you submit sample, then you got the spectra or spectrum. You always have already the value of the frequency for different types of chemical bond. So this is just the basic calculation of it. Okay, so even with the same chemical bond, okay, different types of chemical bond will have symmetry or asymmetry stretching. So for instance, like carbon dioxide here, you have symmetry stretching, means the oxygen will move apart, okay, further from the carbon atom together, or in a left and right motions, then it creates anti-symmetry stretching vibration. So for FTIR, the chemical bond must be asymmetry, okay, or anti-symmetry instead of symmetry. Okay, that is the first requirement for FTIR. If you have anti-symmetry, then they will have absorption of IR. Okay, like this one, there will be no absorption in terms of IR, but you still have anti-symmetry stretchings for carbon dioxide. So carbon dioxide is one very crucial compound in FTIR. So it would create a lot of noise because we have carbon dioxide in the atmosphere that would disturb the signal. So later I will explain to you how to get rid of this signal. So like water molecule is also one chemical compound which is very polar, okay, and you have one oxygen and two hydrogen, okay, because of the configurations of the atoms. It's not symmetry, okay, it's not symmetry. They have polarity, so more negatively charged, okay, and this more positive. So eventually you have dipole moment, okay. That dipole moment will makes the structures non-polar, and they will vibrate, okay, or they will stretch asymmetry, okay, like this one. Then eventually there will be IR absorptions for water molecule. So you see two different stretching behavior. One is symmetry. This one, these two are symmetry, but because the water compound by itself already not symmetry, okay, it's a polar molecule, then they will absorb also IR. Then for this anti-symmetry stretching, the absorption is at 2300 wave number. Okay, so same compound, same molecule have more than one absorption wave number. Okay. So IR absorption only occur two in criteria. Number one, the IR radiation interact with the molecule undergo a permanent change in terms of dipole. When IR interact with this water molecule, the molecule with the vibration of molecule, okay, the atom will interact with the IR wave, and it changes the dipole moment. Okay, it changes the dipole moment of it. So that would be IR absorptions. Okay. Second, incoming IR photon has sufficient energy to afford the transition to next vibration energy state. So when the energy of IR is high enough, then it will be transitions, okay, of vibration energy state of that particular molecule to high level of energy level. So that is a two requirement for IR absorptions. So I give you two examples. Number one, nitrogen gas and also oxygen gas molecule. There will be no absorption because they are symmetry. There is no dipole moment inside the molecule for this nitrogen atom molecule and also oxygen molecule. You try to imagine if the wave coming, the IR wave coming, there will be no change of dipole moment onto the this nitrogen molecule and also oxygen molecule. Then there will be no IR absorption. So means FTIR is not a suitable method for you to detect this kind of bond. Okay, so another example, which is positive example, carbon oxygen, okay, carbon oxygen bond. And you see this molecule, okay, has dipole moment. Okay, they has dipole moment. So when IR is coming, okay, then the IR will change the dipole moment. So it fits the first requirement. The IR interacts with the molecule and create permanent change in dipole. Then there will be IR adsorptions. Okay, so for this slide, the important message is the compound of the chemical bond that you are interested in must have dipole moment, okay, and it will interact with IR, okay, then adsorption will happen. And the IR photon, okay, the IR radiation must have sufficient energy, okay, to try to create transitions, okay, of to higher vibration energy states of the molecule. Okay, so another schematic, I think basically just same like the previous one. So I just I can go quickly. So carbon dioxide, carbon and one carbon and two oxygen, not IR active because this is there is no dipole moment. Okay, if you have for this symmetric stretching, no signal from this stretching, but if there is for bending, okay, because bending there are dipole moment, so this is IR active. Okay, same go to asymmetric stretching dipole for carbon dioxide. So carbon dioxide is again, carbon dioxide is one compound which always interrupt the signal. Okay, so let's go to instrumentations. So I show you this figure just now. IR band, okay, IR photon, or IR wave, different wavelength, okay, different wavelength, passing your sample. Some absorbed by your sample, by the chemical bond, the functional group, okay, then disappeared, and some not, okay, some still can passing through, no absorption, then we detect the signal. So this is called transmittant FTIR. There are different modes of FTIR. So this is transmittant, the most widely used and most common FTIR. So basically your sample is sitting in between the IR source and also the detector. Okay, very straightforward, just like UV-vis, okay, UV visible spectrophotometer. The sample sitting in between the light source and also the detector. So we use a Bessel law to Lambert law to do the estimation, also calculations. So in FTIR instruments, there are different components. Okay, important components. There are a lot of minor one, but this figure only shows important components. Definitely, the IR source is the most important part. So followed by interferometer, Blinn splitter. Okay, you have a lot of mirror inside. Then your sample compartment, then followed by detector. Okay, this is in general an FTIR spectrometer contain this important component. Let's go into the detail. So what is IR source? IR source basically is I think one most famous one is silicon carbide. Okay, so you use voltage, high voltage, high current voltage, then it will heat up. Okay, silicon carbide will generate heat, photocurrent effect, then it will irradiate IR source, okay, IR band or IR photon, and it will go into the specimen. So the name is global, okay, global, and it actually is the silicon carbide. Okay, so let's move on to the next important component, interferometer. Okay, interferometer is the core, okay, or core of FTIR. It differentiates conventional dispersive FTIR with Fourier transform FTIR, Fourier transform infrared spectrometer. So interferometer is the components that introduce signal manipulations, okay, so that you can obtain interferograms from the light, okay, before the light passing your specimen. So what is inside? What is inside the interferometer? You have the light from IR source, okay, the light from IR source. So the wavelength is in mid IR, 400 to 4,000 wave number or 5,000 wave number. Then you have a beam splitter. So the beam splitter normally divide the light into 50-50. One go to the fixed mirror, okay, another one go to a movable mirror. This movable mirror will move at different length, okay, it will move different steps, okay. So this kind of mechanism will introduce interferometer because of the moving mirror actually will offset the IR light. And when the signal from the fixed mirror and the movable mirror come together, overlap, then there will be interference, okay, either constructive interference or destructive interference. So this interferogram will passing through the sample and go to the detector. Okay, so the IR beam is split and direct at fixed and moving mirror. So 50-50, as I told you just now. Okay, since the moving mirror creates offset of the wavelength of the IR light, then they will have, I told you just now, interference between these two waves, IR wave. Okay, then they recombine and go to your sample. Okay, so it will generate the spectrum, okay, after these two beams passing through your sample. This is the function of interferometer. Okay, so in a most clearer schematic, so when the signal, okay, when the IR, the 50% IR from the fixed mirror and the moving mirror overlapped, that it passed through your sample, then the instrument will do Fourier transform to the wave, and eventually it will generate the IR spectrum here. Okay, so what actually happened here is the interference, okay, that requires some kind of algorithm, okay, to generate the important signal from your sample. So this is called interferogram. Then Fourier transform of the interferogram yields the FTIR, the IR spectrum. Okay, so what actually Fourier transform mean? Fourier transform means the computer will convert the spectrum from time domain, because the moving mirror actually moving in terms of time, how much it move, the velocity of the mirror. So the signal actually in time domain. Then after we carry out Fourier transform, the computer carry out Fourier transform, then it will be in frequency domain. So the signal, the plotting will be in frequency domain, which is wave number. So Fourier transform infrared actually improve a lot and solve a lot of disadvantage of conventional dispersive IR spectrometer because of this mechanism, this interferogram, and also the Fourier transform functions. So we have actually maximized the and also increased the resolutions of the spectrum obtained from your sample. Okay, so what is that actually? So in detail, when you have signal from sample and also reference, there will be overlapping and they will have interference. So when these two signal, one is from the background, okay, without passing is from the fixed mirror. Then another one is from the moving mirror. Then interference will happen. Then after passing through a sample together with Fourier transform, then the signal will convert into frequency. So this is actually the dot, the peak that appear in in the spectrum that you obtain from FTIR. So if you have you would like to know more, I think the full explanation actually in these two videos. So I will share the slide later. I think these two videos explain it quite clearly how interferograms and also Fourier transform is conducted in FTIR. Okay, long story short, okay, you have background signal from because when you carry out FTIR analysis, you will always run one measurement without sample, which is the signal from the sample compartment without your sample inside. Okay, and the second run will be always you insert your sample, then you run, then there will be two interferogram. Okay, two signal, okay, two interferogram. Then Fourier transform into FTIR spectrum, okay, from time domain into frequency domain. Okay, then background corrections, okay, background corrections to obtain your spectrum. Okay, so this is the I think it will be much easier to explain this figure rather than going to the interferometer. Okay. So in FTIR spectrum, when you receive the result, you can either plot it in transmittant or adsorbent. Okay, both are actually the same, generated from the same set of data, just different calculations. So you can see they are kind of mirror image, okay, mirror upside down with the unit of y-axis transmittant and also adsorbent. So means for transmittant spectrum, this is adsorbent. Okay, so going down means this is the intensity of the adsorbent. Okay, if the y-axis unit is transmittant, then this height is the signal of the value of adsorbent. Same goes for adsorbent unit, the height is the intensity. Okay, so intensity is something to do with concentrations. Okay, but it's not really directly proportional to the chemical functional group or the chemical bonds that you are studying. So don't confuse this, because a lot of students actually they thought you can use the intensity, okay, in this intensity to tell the concentration. It's not that straightforward. Okay, I'll explain to you later. Okay, so when you receive this data from the operator, okay, in X and Y file, or all the value X and Y in two columns, then you want to convert it into adsorbent. Their calculation method very straightforward. So adsorbents equal to minus log transmittant percentage. So the T is intensity of your sample over the intensity of the background, which is 100%. Okay, 100%. So this is adsorbent minus log your sample over intensity over intensity of the background. So A is adsorbent, T is transmittant, then I is intensity from the sample, then I naught is intensity from the incident light, which is 100%. Okay, always 100%. So we solve this equation. Okay, so when you solve this equation, you have the final equation equals to A equal to 2 minus log percentage of transmission. So example, let's say you receive this result. So for instance, like this value is 50. Sorry, you see, okay, 56, for example. This value is 56. You want to convert it from transmittant to adsorbent. Then the formula is is equal to 2 minus log 56. Then you have 0.252 adsorbent unit. So adsorbent unit doesn't it's meaningless actually. It's just mathematical calculations. So but it's directly proportional. Okay, you can say that this adsorbent unit is lower than this adsorbent unit, but you cannot say You cannot use it for others, for comparison. Let's say you have another study done by another student, then you use that as a way you need to make comparison. There's no, you cannot do that. Okay, it's wrong. So you can only compare among your sample. Okay, and that intensity is directly proportional to the intensity of the chemical compositions, okay, or chemical bond in your sample. Okay, so examples of FTIR spectrum. This is one I got from, I think, from the database. So in transmitted y-axis, then X is in wave number from 4,000 to 400 wave number. So what does it mean? So normally when a FTIR spectrum can be divided into two, one is functional group region, another one is fingerprint region. So in functional group region, you have less, okay, lesser peak, lesser absorbance band compared to the fingerprint. So normally what we can have here normally is OH and also maybe some amine here. So this area, okay, this region basically cover chemical bonds or functional group which are high in terms of the vibration frequency. Okay, so this is for OH, amine, okay, amine functional group, and H2. Okay, those functional group are high in terms of the vibration frequency. Compare with the fingerprint region, it's more complicated. Okay, this is something you need to really be careful. Okay, if you did wrong analysis, then it may lead you to wrong discussions because there are a lot of overlapping, okay, peaks, and they are very close with one another. If you notice the table I showed you just now, the frequency or wave number of functional group is in range. Okay, example, this one, this band, this is a carbonyl group. Okay, carbonyl group is actually is a in a range. It's not one straight line. Okay, in the range. So if you have range and range of different functional group, then they must be overlapping. So you need to do it carefully. Okay, so the pattern is more complicated. Okay, difficult to pick individual bond. So we always need some maybe database software or maybe comparison with previous publications. Okay, so this region is the most important region compared to here because lesser signal here, more signal here. So, and because different compound produce its own unique pattern of peak. So such just like fingerprint. Okay, fingerprint. So if you have organic compound, carbon, oxygen, hydrogens, then if you run FTIR, then you need to focus on this area. And eventually, when you receive this data, this spectrum, you need to focus, zoom in this area in your plotting for you to easily see, okay, each absorbent peak. Okay, so when you have the spectrum, you do identifications, okay, of the functional group. So especially when you receive a signal which is very complicated, a lot of noise, then first thing you can either use software or program supplied by manufacturers like this one, Omic. Omic is a software supplied by Thermo, okay, Thermo Fishers. Then this program is very powerful. Normally come together with the FTIR instruments. Maybe the technician or operator, instrument operator, will have the access, okay, and the program could be installed in the computer. If you have the access, then it makes your life easier because they have database, and they even can the software can do spectral analysis. They can help you to do the baseline corrections. They can do smoothing. They can help you to do normalizations. Okay, can normalize the peak, okay, the spectrum. And Omnic come together with a very big database, okay, for different types of materials. Like if you are doing ceramic, or you are doing polymer, metal, okay, or pharmaceutical compound, drugs, okay, they have the database for different types of material. Then you can easily match with the database, and immediately you know what are the compound presented in your sample. That is the more ideal case, but I don't think everyone has the access of this software or this program, and very expensive. You want to buy it separately. So I think my advice is, if you send a sample to FTIR, you ask the technicians or operator whether they have this software, then at which computer, then you get the permission for you to use it. And this is more important, especially when you are running unknown sample. Okay, for known sample, for example, you are doing chemical synthesis or polymer synthesis, you already know roughly what kind of material you are synthesizing. So then you may not need that software, because you already know that I know this is polypropylene. Then I think the software can't help you much, right? So if you receive some sample, unknown sample, you don't know what is that, then you may need this software to help you in analyzing the spectrum. Okay, and the software can even tell you the similarity. For example, for unknown sample, then you get the spectrum. Okay, you get a spectrum. Then you ask the software to do the matching. Then the software run the data, check with the database. Okay, this is the possible spectrum, spectrum that match, let's say 85% or 90%. So it can tell you the similarity percentage. Very powerful tools. Okay, and this is widely used in industry as a QC tools for quality checking. Okay, and the software even can help you carry out to calculate the intensity area under the curve, because information such as area under the curve can help you to estimate. For example, in polymer study, you know the crystallinity. Okay, not only XRD can tell you crystallinity of your sample, FTIR can also do that. Okay, so and many more, many functions. Okay, many functions of it. If you do not have this, okay, the software, you don't have the access, it's fine. You still have other options. Second one, you can consult reference table or database that provide information on the expected frequency and intensity, like the table I showed you just now. For example, I show you this one. Yep, like this one. This is on Thermo Scientific. I can just download it from their web page. It tells you the different functional group, what would be the possible band, adsorbent band. For example, methyl, methylene at 2090. Then we go to the fingerprint region. So this is here, oxygen group, ether, alcohol. Okay, so you see, remember just now, OH, higher frequency. Okay, because they are very polar, high in terms of dipole moment. So same OH, then CO, okay, CO group. Then carbonyl group, okay, carbonyl is one of the very important functional group and very sensitive to IR adsorbents. Carbonyl group in aldehyde form, in ketone, in ester, and also carboxylic acid. Each of these has their own adsorbent band, but some very close with one another. So this is very dangerous. Okay, very dangerous for you to do the fitting or identifications. So it always helps with another signal from other functional group. If you know your roughly know your the sample. Okay, so and nitrogen group, amine. Okay, I told you just now, amine is also another functional group with high frequency, same like the hydroxyl, this hydroxyl. So they always overlap with one another. So this is something you need to also be careful. Very close, 3,350 for OH, 3,300 for amine. Okay, for amine. Okay, so The second option you have, I told you just now, you can compare with this kind of table to do the fitting. Third one, you can refer to journals, articles, because I think most of the researchers are kind enough when they write research manuscript, they will explain every single page representing what kind of functional group, and you cite that particular journal's article. This is also possible. And also guides. Okay, I just noticed recently there's one nice guide from this link. It actually explains or guides you how to interpret your FTIR spectrum. So this is the link. You can click from here. Then this is the website. So they have procedure, okay, step by step. Then it can even teach you if you have, let's say, this problem. This is a spectrum. Okay, this is a spectrum. Sorry. Okay, problem number one, for instance, you have this spectrum. You don't know whether this is this one, or this one, because all these five functional group, 5 compound contain C double bond O. Okay, so you don't know which is which. Then this website actually explain to you how to screen, okay, how to remove, okay, from here, you know this is not possible, and how to choose the right functional group. And they have a lot of actually example listed in the website. So if you encounter this kind of problem, I would advise you to refer to this website. Very useful. Okay, very useful. Okay. So before that, okay, before you go to do all this matching, okay, so you should learn how to, first thing, how to plot the FTIR spectrum, then how to process it. This kind of spectrum is low in terms of quality and very poor. If you plot your FTIR in this way, and highly possible your manuscript will get rejected, or maybe the examiner or your thesis reviewer will comment, okay, or maybe will criticize your result. Okay, so same like what I explained in XRD topics last week. I highly recommend students use Origin Pro software to plot your FTIR and also to process. Okay, so I would like to emphasize here, processing of spectrum or diagram or analysis result is not manipulation. Okay, it's not manipulation. You are trying to improve the spectrum quality, not changing the data. Okay, so people always have concerns about if I make baseline corrections, is it allowed? Is it something forbidden or prohibited? No, it's fine. You can always do background corrections. Same example goes to the software that I explained to you just now. When you have this from Omnic, from Thermo Fisher's, the dedicated software, this software will also have the function just by one click. Then you can immediately baseline correct your spectrum. Okay, this is something allowed, and you are advised to do so to increase the quality of the spectrum. Okay, so I put a link here. Okay, but I think I will maybe do a demo. Okay, quick one, explain to you roughly how to do this kind of baseline corrections and also smoothing. Let me get out from PowerPoint. Then I will go to Origin. So I'm not so sure whether you can see my screen because I cannot enlarge it. So can I confirm whether you can see all the my Origin Pro page?
Yes, we can see, Prof.
Yeah, thank you, Nishara. So okay, I will go to my the data. I got one example spectrum I received recently from my student. So X and Y, okay, to X and Y. X is a wave number, Y is the intensity in transmittance mode. So let's go to here. So I will paste the value here. So Y is wave number in centimeter reciprocal. Sorry, this is the value. This is the then the unit is centimeter reciprocal. Okay, X is the wave number, sorry, X is wave number, and then Y is intensity, is transmitted. And the unit is percentage. If you have adsorbents, then you just type adsorbent. Okay, then I can plot it. I just highlight these two columns, then can plot it. So I have the spectrum. Not really, I think not too bad. This one, the adsorbent is kind of low here, only up to 70 something. So what the first thing I need to do is I need to change the scale. I need to make this x-axis from higher to lower. Okay, make it reverse, because normally FTIR is plotted in that way for reasons. Okay, so I plot from 4,000 to, let's say, 600, because the signal is quite kind of poor here. This would be I consider this as noise below 600, so I will just plot in 600 from 600 to remove the noise. And I think it's fine for me, because my concern is not at this region. Okay, the specimen that I am studying is not important here. So that is for horizontal. X-axis. Let's go to y-axis. Y-axis should be from 100 to nearly 75 to 100. Okay, so this is the spectrum after I change the scale. Okay, make it nicer, more clearer, so I can do the baseline corrections accordingly. Okay, so a lot of noise here, you see. Okay, a lot of noise, and also the background is not, baseline is not really nice. The right better spectrum should be background very high. You see, this background comes to so low. Okay, then we need to move it up. Okay, shift it to here. So how to do? We go to analysis. So we go to peak and baseline. So you go to hang on, peak and baseline. Say to okay, peak analyzer. Go to open dialog. Okay. So you open up the peak analyzer. So we create, okay, create baseline. Okay, now we need to create baseline. Go to next. So I will stick to this second deviations. Okay, second deviations. Then by default, where I need to, the system will by default choose 8. Okay, 8 point from the baseline to do the calculation. So yeah, is it gone? Where is the signal? Let me reopen again. Yeah, try again. Create baseline. Then by default, the system will give me 8 point to choose the location of the baseline, but I want to have more, because the spectrum I have is kind of bit poor in terms of the quality. Okay, the baseline. So I increase up to, let's say, 12. Okay, 12. Then I click next. So the software will by default choose the possible background, but this is not the right one. So I want to I can add if I want. Maybe I can add here. Okay, I can add here more point. Let's say this one. I double click. I want it to be here. One. Then maybe here I already have. Then maybe I need one here. Maybe I need another one here. Then I click done. Then in total, I already have. In total, I have more. I think I have 15. Okay, 15 point. Okay, then I need to modify the location of the dot. Okay, or this point. This shouldn't be this low because I know that this is OH. This peak should be broad and also high intensity. So I increase the background here. So the line should be above the spectrum. Okay, the line of spectrum. Sorry, the dot. The point should be above the line of the spectrum. Okay, same to this one. Okay, here, so I know this shouldn't be the allocations. Okay, so here, maybe here a little bit. Okay, then here. Okay, so I think this should be fine. Okay, so I click done. Okay, done. Then finish. So the computer, the software will give you the baseline. Okay, a baseline. Then once you have the baseline, then you need to process the signal. So, let me check out where is the. Okay, you go to data manipulations, subtract from preferred data. Okay, then you choose the baseline, the line that you created just now. Okay. Okay, then this is the baseline. Then you go back to the project explorer. Then you click the book one. Then you have one additional column that with the name of baseline corrected. Okay, then you replot the spectrum. No, this is not. So this is not the right one. This should be the one. This one. This one, the spectrum baseline corrected, subtracted by the baseline. Okay, now you have the new one. Okay, you have the new spectrum. So I will do the same thing. I need to change the scale. So the vertical. Oh, this is wrong. This is not the one. This should be in other form. Hang on. But why the unit still? Okay, it's fine. I change it first. Okay, I change the scale. Vertical still the same, 75 and 100. Oh. Don't. I delete this one first. I plot it again. I'm sorry. Okay, 4,600, and this should be okay. Okay. From zero, from my the scale change already. You see, after doing the after conducting the baseline corrections, then the scale changed. So it should be 0 to -25 roughly. Okay, roughly you can try. Okay, so you see, compare with the previous one, this background, this side here already shift up. Then the baseline of your spectrum is much nicer compared to the previous one. Okay, so what I would do, I would normally delete the unit here because it's in arbitrary unit, and because you have conducted the background subtractions, baseline subtraction, so the unit no longer relevant. Okay, so now the spectrum look much better, but you still have the noise. You see, the noise still very high. So what you can do is you can do smoothing, okay, spectrum smoothing. You go to analysis again, you go to data, you go to signal processing, smooth. Okay, so this is smooth. The function that you can use. So you can click auto preview. So this is the original one. What you have now here. Then what you can do, there are two places you can try. You can increase the points of window. So means 5 points. 5 means the computer will take 5 point, nearest point, then take the average. Basically, smoothing is averaging. Okay? You take how many points, then you take the average, then that is considered as the average point to use for the 5 consecutive points. So means the higher the points of window, the value, the smoother the peak. But you need to be careful. If you use too high figure, if you put, let's say 100, then you may lose the resolution of your spectrum. So what you need to do, you need to try, let's say, slowly increase from 5, let's say, to 10, 15, 20, until you have what you want. Okay, or the second one you can try is to increase the polynomial order. Same, the higher, the smoother. Okay, so both you need to try together and generate the spectrum that you want. Maybe you can use 5. I choose 20, for instance. I preview. Okay, if I think this is okay, because it is too small to see, so maybe you need to enlarge it. Okay, you need to enlarge it. For example, I try, let's say 40. I preview. Okay, slowly. Then this is 5. This maximum is 5. And the value of point of window always need to higher than the polynomial order value. Okay, so put 5, then you can put this 5, then you can increase the value of this. Then once you are satisfied, then you can click OK. Then the spectrum is processed and show it in here. Then how to extract the spectrum after smoothing? You go to Project Explorer, you click another book 1. Okay, another book 1. Then you have the smooth spectrum. Okay, this Project Explorer is you can always find the new spectrum generated after each function that you do from the Project Explorer. Okay, then you know this is smooth spectrum. Then you repeat the plotting again. Okay, the plotting. I think there should be a way to, I don't know, when I check some versions of Origin, they are much more convenient and easier, but mine, I need to replot it. Okay, I need to replot it. So this is the new spectrum. Okay, smoother, much smoother compared to the previous one. You see, the noise is okay, improved. So I will repeat again the plotting, actually the scale. So the vertical one from 0 to -25. Okay, so this is the smooth spectrum. So after smoothing, before and after, you can see the difference. But there's no book of recipe or cooking recipe for you to do, and different person will have their own preference until which level they want to smooth their spectrum. And not only one spectrum, to decide to which level you smooth the spectrum really depends on, also need to consider other spectrum that you put together and make comparisons. Okay, that's how you do the baseline corrections and also the smoothing. Okay, so you can change the label of the y-axis wave number in centimeter, 1/centimeter. Then this is transmitted in percentage. Okay, so you remove the value of the y-axis. Then you go to view, then view, and you go to the frame. Okay, so you have a frame normally for the format of publication. Normally we have the frame closed, then you can label. Okay, origin software come with a lot of functions. Okay, a lot of function. I think I got one. Please share the authentic link to publish review papers. So I'm not sure what does it mean, but can Sabita, can you be explain a bit about your comment in the chat in case I got you wrong, the meaning. I think I shared the link, right? I think most of the reference or figure I use, but if I overlook, so I might apologize. Okay. Okay, so this is example how to do baseline corrections and also to carry out smooth functions for your spectrum. So if you have any problem, so you can ask, or I think there are more than this the functions of to use origin. I think other people also, I think a lot of YouTuber, a lot of researchers actually they share their experience and in YouTube, and they have their own channel. I learned actually from the channels, so you can also follow the same practice. Okay, so not only baseline corrections, not only smoothing, so origin can also do many more functions, and you can learn how to plot FTIR spectrum in a more professional way. Okay, so I give you example of not so nice spectrum. When you have this, then you send this as a spectrum in your research manuscript. Too messy, okay, too messy, and the plotting is also not correct. This should be here. Okay, so more example here. This one, you see the background, the baseline. Sorry, the baseline is not really nice. Okay, and this one also. I'm not saying this is wrong, but can be improved. Okay, and this one, so you hardly see the difference. Okay, I give you one good example. I think this is good enough. Okay, so this is plotted using origin, I believe, or sigma plot. Okay, so the signal is I'm confident that this spectrum has been also baseline corrected, and also after the smoothing, so and plotted in a nice way. Then you can have the dotted line to show where is the absorbance band. Okay, which absorbance band you're interested in, and supported with the discussions. Okay, same goes to this one. Okay, so another figure, which region, what kind of functional group. Not only this figure, I think you can find a lot more, but I just give you a couple examples. Okay, any questions from the students or from the audience before I continue?
Any question from audience? I think, Prof, you can continue. And for Savita question, I think she might wrote wrong thing. Maybe she would like to know about where we can get a review paper or publish review paper in good journal, something like that. So we have actually, we already had 2 classes. You haven't joined it. I will share the YouTube link of our class so you can get idea actually where you can publish. Thank you. Thank you, Prof. You can continue. Or Prof, do you go for 10-minute break?
Can I think we can go for
Okay,
10-minute
so
breaks.
now it's almost 10:20, so we'll back 10:30. That means in new time 11:30.
Okay, yep. Thank you, Ms. Shara.
Okay,
So I'll see you
okay,
all
thank you, bro.
later. Thank you. Hi, Mr. Shara. Can we continue?
So, Prof, yes, we can continue, Prof.
Yes, thank you. So welcome
Thank
back.
you.
So I just project. Okay. Just now I did mention that for a chemical bonds or functional group to absorb IR, it must possess a dipole moment. Okay, but dipole moment. So for instance, like oxygen, hydrogen. So they are polar, so they have dipole moment. So the magnitude of the dipole moment depends by affected by charge of the atom, each atom. So the more higher the charge means that the higher the difference between the charge, the higher the dipole moment, and the longer the distance, okay, far apart between these two atoms, then the higher the dipole moment. So the higher the dipole moment of a chemical bond means the more the more changes of the dipole moment when this functional group or chemical bond exposed to IR, then it will absorb more IR. Okay, example here, OH. So I always I tell you I think a couple of times just now, O hydroxyl OH group absorb the highest frequency of the IR. So they appear as at the highest wave number. So remember, wave number means frequency. The higher the wave number, the higher the frequency. The higher the frequency, the higher the bond. Okay, so when you have higher dipole moment, then you will have the greater the changes in terms of dipole moment when it exposed to the incoming IR. So I repeat again, when this chemical bond has high dipole moment, it will respond to the incoming IR and absorb the highest higher IR signal. Okay, you will absorb the high IR's energy. Then the intensity of the band will be higher. And the greater the change in this, and the more the intense the absorbent band. So this is the factors that affect the absorbent. So if you come to this table, OH is the highest, then followed by amine. Okay, amine. Then only goes to the carbon bond. Okay, and the more the bond, like carbon nitrogen triple bond, carbon triple bond, carbon double bond, carbon nitrogen double bond, and also carbon with double bond oxygen. This is also higher in terms of energy compared to carbon oxygen single bond. So the more the bond, okay, triple bond, double bond, the frequency, okay, and the absorption energy is higher compared to single bond, except this one, okay, except this one. So we don't normally we just ignore this, okay? We will just look at the carbon bond at this region. If you should remember, FTIR spectrum consists of two regions. One is the most important is the fingerprint region, okay? Fingerprint region, which is in between here from 1100 to 1800. This would be the fingerprint region. So since OH is the most polar, okay, most polar because of high dipole moment, then it will higher in terms of polarity compared with CH, C and H. Okay, so and it is highest in terms of polarity, so it will change in terms of changes in terms of dipole will also be the highest as compared to amine and also C and carbon and hydrogen. So the signal, okay, the IR absorptions will be also much higher compared to another one. So if you look at example of FTIR spectrum, OH, not this sample. Okay, this sample contain very less OH, so this is very low, and the CH stress is very high. This should be polyolefin sample. Be a polyolefin, for instance, like polypropylene, polyethylene. So you have a lot of C and H functional group. Okay, so what are the advantages of FTIR compared with UVs, XRD, and others analytical instruments? First one is speed. Okay, if you have experience running FTIR analysis, is a quick process. If without sample preparation, I think just few seconds or within a minute. Okay, from the time you place your sample in onto the sample the sample holder, then in just a few seconds you can obtain the spectrum. Okay, if include sample preparations, let's say you prepare your sample, you mix your sample with KBr, potassium bromide powder, then you compress it. It could be maybe few minutes, maybe 10 to 15 minutes. Okay, so it's still considered fast if you compare with NMR, if you compare with, let's say, DSC, okay, and maybe others instrument. FTIR is considered fast in terms of analysis time. The sensitivity has been improved a lot. Maybe if you talk about dispersive infrared spectrometer a long time ago, yeah, the sensitivity is very low. But now, thanks to the interferometer and also the Fourier transform functions introduced to infrared spectrometer, the sensitivity increased tremendously. Okay, and if you carry out the analysis properly, carefully, and you control the humidity, you prepare your sample nicely, then you can actually reduce the noise. So you can increase the signal to noise ratio. Okay, and that would be from there you have a good spectrum for you to further interpret to get the result. And mechanical simplicity. So it looks complicated, a lot of optical path, because optical path is something already fixed and firmly installed in the instrument, and it's not a problem anymore in FTIR. And the only moving parts in FTIR instrument is the moving mirror. Okay, the moving mirror, whereby to create the interference and then to produce the interferogram. So this is the moving mirror. Okay, bin splitter. Okay, bin splitter. Then one come back, then the moving mirror overlap with the fixed mirror IR, then go to the sample compartment. Okay, go to the sample compartment and detected by the detector. So the only moving part is here. So it's not a big issue. So it's very stable instrument. Okay, so very little possibility of breakdown. But one important things about FTIR, especially the sample compartment, is the sealing. Okay, it must be closely enclosed. How to say? The enclosement must be good enough to avoid carbon dioxide and moisture gets in. Although you can do background scanning, but if the fluctuations of moisture and carbon dioxide concentration in the sample compartment change a lot, then it will affect the quality of the signal. Okay, then the internally calibrated. Okay, if you look at this figure, there is one laser besides the IR source. Okay, the glow bar, the silicon carbide glow bar provide the IR. Besides that, you have one helium neon laser. Okay, helium neon laser serves as the reference laser with the wave number of 632.8 nanometer. So this is a reference laser, reference light for the instrument to do calibrations every time when you do the measurement. Okay, so FTIR is a very reliable instrument nowadays, not like last time, especially on the dispersive infrared spectrometer. Now this instrument is very versatile and very stable because of the all kind of additional features or additional component installed in the instrument. So these are several examples of advantages for FTIR. Okay, there are wide ranges, different manufacturers. Okay, you can name it. I think you should have also experience in using or sending sample to different brand or model of FTIR. So this is from Agilent. Agilent itself, the company produce different types of FTIR, ranging from handheld. You can have handheld FTIR, like handheld XRF, handheld Raman. Okay, FTIR has also handheld. You can carry it and bring to the field to do a site measurement. Then benchtop. Okay, benchtop, small one, and even bigger one. Okay, with microscope. Okay, with features that you can also measure FTIR under FTIR analysis under microscope specimen. That is also one nice features. A lot of interesting results can be obtained from here. I will share with you some example. Okay, and many more. So as I told you just now, there are different types of FTIR instruments from different manufacturers, and they have different models. At the same time, they also have different modes of FTIR measurement. Example, transmission. The example I give you, I think the most common one, transmission FTIR. So IR source, passing your sample, then detector measure whatever left over. Whatever disappeared means absorbed by the specimen. Second popular, ATR, attenuated reflectance, FTIR. So the wave, IR wave, have experienced total attenuated total reflectance inside a crystal. Okay, different types of crystal. Then it produces wave close to the surface of the sample, up to a few tenths of micron. So your sample will expose to a layer of IR wave. Okay, IR wave, and it will absorb. Then the sample and absorb, then come again and absorb again and absorb again. So it experiences multiple bounce. Okay, on the surface of your sample. Then eventually the leftover signal will detect by the detector. This is also a very popular method, and it's a surface sensitive surface sensitive FTIR spectroscopy. So there are two different types of crystal. One, some is multiple bounce, some with single bounce. So I think very straightforward. Multiple bound is more sensitive because your sample experience different times of absorptions compared to single bounds. Okay, so I will explain a bit further later. Then the third one, drift spectroscopy. Okay, drift spectroscopy. Then this is especially important for powdery sample. If you don't want to have sample preparations, so this is nice. Okay, it's a very sensitive method, and improved versions of transmitted FTIR. Okay, I will explain also. Then another one, reflectance micro FTIR. This is on the small sample, very small surface. This is also another mode. Then there's another very interesting FTIR instrument. We call it photoacoustic spectroscopy FTIR, or PAS FTIR. So we know IR is an electromagnetic wave. So wave, so it's something like sound wave. So you can actually detect it using sensitive microphone, okay, or we call it amplifier. Okay, amplifier. So when sample absorb infrared at different wavelength, okay, different wavelength, whatever absorbed will remain in the sample, and whatever not absorbed, okay, by your specimen will bounce, okay, will reflected from the surface of the specimen, and the signal, the wave detected by a microphone, okay, high sensitive microphone. So detect using computer, then you can measure it. So this is a very interesting instrument. I think not really new technology, but it can measure sample at different depth, okay, different depth of, let's say you have a sample with different profile from the surface, different concentration from the surface down to the bottom. Then you can use PAS FTIR to measure the profile of the specimen. I do not include here, but I think you can find the related materials if you have interest on this. Okay, so let's go to transmitted FTIR first. This is the most straightforward one. So transmitted FTIR carry out two measurements every time when you analyze your sample. The first one you need to do background scanning, okay, without your sample in the background. Why? Because in the sample compartment, when you open it up, okay, to put your sample, you definitely introduce water vapor, okay, and also carbon dioxide from the atmosphere. So as you know, carbon dioxide is a polar molecule. It's not oxygen. Oxygen is the non-polar, so no dipole movement. So it will not absorb IR. But in the atmosphere, water, H2O, and carbon dioxide is the gas that will absorb IR. So you need to make measurement. You need to measure the background and correct with the spectrum that obtained from your sample. So every time the instrument will do two analyses. Okay, the first one from the background, okay, without the sample. The second one, you put in your sample and measure. Then two interferogram, if you still remember, okay, interferogram, the background will also have an interferogram by the interferometer. Then Fourier transform into IR spectrum, okay, then overlap corrections, okay, it will correct the background. Then finally you have your FTIR spectrum in the unit of absorbance. Okay, have to be careful. Absorbance means the signal is going up, transmittance coming down. Okay, so percentage of transmittance is always sample over the background, so times 100%. Okay, so the unit for transmittance is percentage. Okay, percentage. Okay, so normally transmitted FTIR require sample preparations. So let's say you have a crystal sample, powder sample, rock sample, or maybe some wood powder or nanoparticles in powdery form. If you want to run analyze it using transmitted FTIR, this is something that you cannot escape. You need to prepare a KBR, your sample in KBR pellet, okay, together with KBR pellet. So this is KBR powder, potassium bromide. So this is the proportion, the spectrum of KBR. You see the signal is not really so bad. This not KBR is transparent. It will not absorb too much IR. Okay, so it can be easily corrected. Okay, when you run your sample inside a KBR pellet. So this is the reason. So the KBR is just as a substrate to hold your sample. Okay, to hold your sample. Let's say your sample is loose powder. Let's say flour, wood powder, nanoparticle powder, okay, or some geology sample, clay powder, okay, bentonite powder. So it can be easily mixed with KBR powder and pelletize it into a pellet form. Then you can insert into the transmitted FTIR instrument. Then you run the analysis. Okay, so why KBR? Because transparent, mainly transparent. Okay, you see it only absorbs up to 20% of the light. Okay, at this wavelength. Okay, or wave number. The rest, I think, quite stable. Okay, even to IR, far IR region. Okay, so the most widely used material for preparing sample for transmitted FTIR, and is chemically stable. If you mix with, if you use KBR pellet and mix it with your sample powder, it would not have any chemical reactions because it is inert. Okay, it's just like sodium chloride, salt. Some people use sodium chloride. Okay, can also, but the most widely used is KBr. Okay, so it's stable, it's inert, so will not affect the result. Okay, then high refractive index. Okay, the IR can easily reflect inside the specimen, and will not actually reduce the signal. Okay, so the more reflectant inside the KBr substrate, the more chances of your sample exposed to the IR and absorb the IR. Okay, so high refractive index means when the IR light pass through your sample, the pathway is longer. Okay, compared with other types of material that with low refractive index. So means the chances of your sample in the KBr pellet is higher to expose with the IR source. Okay, and easy preparations. Okay, no heating and no does not require special instrument, just very simple one. I will explain to you. You mix your sample powder, let's say your powder sample with a certain percentage, at certain percentage with KBr, then you homogenize it, then you press it, and it become a transparent pellet. It's transparent pellet. So, and as I told you, sodium chloride, so is another possible thing, but sodium chloride absorb quite a high amount of IR. Okay, so KBr is the most suitable one. So these are apparatus that you need. Okay, and if you have experience when you send your sample to transmitted FTIR in the lab, they will definitely will definitely see this kind of apparatus. So you have the mortar. Then for mixing the KBr powder, this is the mold or die that you need to put the powder inside. Then you need a hydraulic compressor. Okay, it can be just a manual one. Then press the powder, and you can directly turn into a transparent pellet. So this is the whole concept of it. You put your powder here, mix well with your sample and the KBr. Then you close it. Then hydraulic press the powder, compact the powder into a pellet geometry. Then it will turn into a transparent pellet. Okay, that's the beauty of KBr. So this is sample holder. You put the your KBr pellet in the sample disk and slot into the transmitted FTIR. Depends on the brand. Okay, different holder design of the holder. This is from Pike. Okay, so this is a video how to prepare KBr pellet. So what are the precautions? Okay, we need to be careful. You need to make sure the different precautions, and you can follow this video. So for IR, for transmitted FTIR, there are different accessories. Okay, there are different accessories. For instance, you can have gas cell. Okay, gas cell. You pass the gas cells in and keep it in this glass compartment. Then place in the FTIR instrument. Then light pass through. Okay, light will pass through the compartment. Then measure the gas sample. Okay, so liquid cell. So you can inject your liquid sample in this window, glass window. Then you slot into the instrument, transmitted FTIR, and you measure the spectrum. This is also possible. Then a different accessory, again, many more. This is from Agilent, and they are different manufacturers like the more Brooker, okay, and many more. So precautions, okay, I go quickly. Precaution when you prepare, when you run FTIR. Sample preparations, make sure it is homogenized, uniform, inside the transparent KBr substrate, okay, and free from impurity. because any organic impurities can easily tarnish or reduce the quality of the spectrum. And it need to be baseline corrected. So this is background corrections, the carbon dioxide and also hydrogen, water, H2O background need to be measured nicely. And normally every measurement, not every measurement, but every time when you turn on the instrument, you need to do background scanning one time before you analyze those samples. And calibrations, this calibration is not something to do with the instrument calibrations. It's basically just for you to cross-check, okay, for you to double confirm the instrument is working at an optimal conditions. I told you just now, the helium neon laser installed in the instruments can serve as the reference laser, so that's 632 nanometer is consistent with the 632 nanometer of the wave, the IR wave. So you can do, it will just correct by itself. That is for the wave itself in the instrument. But this calibrations here is something to do with, for you to double confirm that the signal that you obtain is correct. So we will normally use very simple materials like polystyrene that you can get everywhere, polyethylene, plastic bag, or even salt sample. You can grab it some of the from your lab, the pure high purity sodium chloride, okay, or plastic bag, okay. You can just run and to see the excuse me, the spectrum, and to make sure that this same like the standard reference. Okay, next one is conditions of the measurement. As I told you, temperature, humidity, and temperature will always affect each one another. Okay, so humidity means a high water content in the atmosphere. It will actually create noise to the signal. Okay, so what you need to do is you need to maintain the temperature and also the relative humidity in the lab, in the rooms that you conduct the measurement. Temperature, I think if you turn on air condition, I don't think the humidity will fluctuate a lot. I don't think the humidity and also temperature both will fluctuate a lot. So this shouldn't be a problem. If you don't have air condition in the room, then you may have problem because the temperature in the room could change from time to time. Then cleaning, always remember contamination, especially organic contaminations, will introduce a lot of noise, a lot of additional peaks in your specimen. Like wax, with your hand, let's say, without cleaning properly, you may have wax or maybe oil, sweat, that will affect the result. Sampling, always remember when you conduct experiment, you do research project, you have sample, you have analysis, you need to have duplicate. Same goes to FTIR. So when you run the analysis, before you click run, you have the chance to actually choose how many runs. Okay, let's say one specimen you want it to be to have, let's say, 5 times of full scanning. Then the computer will get the average. It will give you the average spectrum. That is one proper or right way of doing the analysis. The more repeats, okay, the more replicates you have, the lesser, the lower the noise, okay, and the higher the signal of your result. Last one, data analysis. So if you have data analysis is something that you cannot avoid. Okay, you need to do some post-processing, like I showed you just now, baseline corrections, then smoothing, especially for those FTIR instrument with a relatively lower sensitivity. I show you the picture just now. There are different types of FTIR instrument, some handheld, some small size, some bigger size. You can tell from the size, okay? Smaller size, they may use cheaper or maybe smaller sensor or maybe smaller crystals. So lesser mirror, so to increase the sensitivity. So it really depends on the budget that you have sometimes, and also what kind of instrument available around. If happen to be the sensitivity of the instrument is low, okay, then this is the only option that you have. You have no choice. You definitely need to send a sample. And when you collect the spectrum, you found that the spectrum quality is not so nice, with very high background noise, then you have a chance to do the post-processing. But don't overdo it, okay? Do not overdo it, because it may lose some resolutions or some important information from the spectrum. So it's always a balance between what you have and what you want. Okay, so just try your best to generate the best result that you can. Okay, so data interpretation statistic method, okay, to how to compile all the spectrum and make quantitative analysis. That is also very interesting functions or interesting applications of FTIR. I'll show you a couple of examples later. How to use FTIR to do quantitative detections of certain chemical or certain compound in products in the market. So second, attenuated total reflectance, FTIR. So, or we call it ATR. So we have this in the lab. So, and this is the smallest I can see from Brooker. Is the sensitivity is not really high compared with bigger size model, but it's small and easily carry. Then it's very simple and very robust. So different company, Brooker, Thermo, Scientific, and this is from Berkeley Element, and different crystal. So attenuated total reflectance, as a figure I showed you just now, is the light, IR light, will reflect a couple of times in the crystal or single time, depends on the crystal that you have. If you see this very long crystal, then this is multiple bounce crystal. Okay, and if you see the crystal is small, then you know this is maybe single bounce crystal. Okay, easily tell from the size of the crystal. This yellow color is zinc selenite crystal. Okay, so what is ATR? So I told you just now, single bounce, multiple bounce. Okay, so total attenuated total reflectance mean the IR source, IR light will reflect. Okay, completely reflected inside the crystal. And because of different reflective index between your sample, the green color one is your sample surface sample, the yellow color is the crystal. Because of different reflective index, it will generate a wave, we call it evanescence wave, at a very thin surface above the crystal, okay, up to few tens of micron, okay, on the surface of your sample. So I told you just now, ATR is surface sensitive analysis. So because of this evanescence wave, okay, so the more the time bouncing time, okay, the more absorptions. Okay, so like this one, the IIR, the sample has a chance to absorb 1 time, 2 times, 3 times, 4 times, 5 and 6 times before the IR beam goes to the detector, and you read how much IR wave has been absorbed by your sample. So definitely this is more sensitive because more time, okay, more time of the absorption by IR absorption by your specimen or your sample. But this one only one time. So what is the why people design this way? Why don't you use this? So there are reasons. This crystal is very big and very expensive. Okay, big crystal, bigger sample compartment, bigger instrument size. If you have small crystal, cheaper. Okay, I'll give you an example. There is another example of crystal material used is diamond. So how expensive is diamond? You can imagine. So if you use a very big diamond, something like this, compared with this size, then this would be very, very expensive. Okay, so there's the reason. So basically just to cope different range, different customer, how much budget do you have. So this is what we call internal reflectance. So the degree of the IR beam going through your crystal is very important. Okay, so the depth of the penetrations of this IR, okay, depends on couple of parameters. The wavelength. So from 4,000 wave number to 400 wave number, that is the wavelength that you need to key in. So from that means when the IR instrument scan your sample at different wavelength, okay, you change the wavelength from 400 wavelength wave number to 400 wave number to 4,000 wave number, the depth of the scanning will be different. Okay, but it's still within a few tenths of micron, so we consider that as a volume of scanning. Okay, so to achieve this internal reflectance, there is a critical angle required. So this is really depends on types of crystal and also the configurations of the design of the crystal geometry that you do. Okay, so big crystal meant for bulk sample. Let's say you have a block of let's say polymer. Okay, big size, you can directly put on the crystal and press it a little bit so that the contact they close to the crystal. Because always remember, this wave, evanescent wave, is only few tenths of micron. Okay, so the sample has to be contact closer to the crystal. Okay, so this evanescent wave penetrate into the sample, then absorbed, okay, by your sample. ATR, FTIR is very, very versatile. No sample preparations. You do not need to prepare KBR pellet. Okay, you need to use KBR as the substrate. No, you can directly place your sample on top of the crystal. Okay, this is small crystal. This is also small crystal. This is big crystal. Okay, then you just clamp it. This side will press on your specimen, the sample powder, and make sure it's contact, okay, on the surface of the crystal in order to absorb the evanescent wave. So it can be powder, it can be liquid. No gas sample. Okay, ATR is not possible for you to analyze gas sample because the molecule has to be, or sample or molecule need to be closely contact on the surface of crystal. If gas sample, gas is volatile, gas is moving all around, then you cannot ask gas molecule to stick on the surface of crystal. Okay, so only liquid and solid sample. Advantages: increased sampling versatility. So solid, semi-solid, polymer, film, you have gel sample. Okay, it can be all is possible. No sample preparations. Very simple. Once you drop it, when you analyze, then finish. You want to run for the second sample. You just use tissue and some, let's say, ethanol or alcohol. You wipe. Okay, you clean the sample holder. Then immediately you can carry out the next analysis. Enhanced sensitivity. Okay, compare with transmitted. Okay, FTIR. because of total multiple bounce. Okay, your sample experience multiple bounce in terms of the evanescence wave. It absorbed multiple times. So ATR most of the time give you better result, but depends. Okay, depends how you prepare your sample and a lot of factors. But in general, ATR is a sensitive method compared to transmitted. Improve signal to noise ratio. Okay, same reason, because multiple reflections. If you use bigger crystal, then ATR will be better compared to transmitted. Improve quantitations. Quantitation, you can do quantitative analysis. Because of this high sensitivity, improve signal to noise ratio, then the signal receive the obtained FTIR spectrum will be higher in terms of quality. And reduce sample preparation time. This is, I think, the most important advantage. No sample preparations, immediately you can do it. Okay, that's why this is what happened in my university. 20 years ago, we have most of the FTIR instrument we have in the university is transmitted FTIR, but now all of the FTIR instrument we have, most of the FTIR instrument we have in different departments or different center are ATR. Okay, for that these particular reasons. Okay, so different crystals: zinc selenide, zinc sulfur, germanium. Okay, germanium is also one good crystals. Okay, like good crystal because of the this depth of penetrations. It's very surface sensitive measurement. If you need very surface sensitive measurement, you need to choose germanium, but very expensive. And silicon and diamond. Okay, diamond is the most versatile one, most stable, most strongest. Okay, it's the strongest one, but very expensive. Okay, and another one is but the penetration depth is quite high, 1.66. Okay, so it means that you actually measure down to 1.66 micron. Okay, so zinc selenide is the most cheapest. Okay, most cheapest, but it is very fragile compared to diamond and silicon. Okay, and scratches. So bear in mind, you are dealing with different types of samples. Let's say polymer sample, I think you'll find. Fiber sample, I think you'll find. If you have rock or sand sample, very hard, then the instrument press the powder close contact with the crystal. That force may create scratches. Okay, scratches on the zinc selenide. If you have scratches, then the light may not able to experience total reflectance inside the crystal. Okay, so you may have noise a lot. So germanium, high reflective index. Okay, so normally used for black sample. Okay, black sample or surface sensitive measurement. Last one, diamond, the most robust. Okay, chemically inert, then will not crack. It will not crack because diamond is the hardest material. So, but this is expensive. Okay, so this is one work we done. That conducted long time ago in 2009. That I use multiple bounce FTIR. This one, something like this. Okay, I have the chance to use it by myself when I did my research attachment abroad. So let's just give you one example. We produce magnetic paper, smart paper, paper with magnetic properties. So, and I would like to see because I conducted synthesis process to grow the nanoparticle, magnetic nanoparticle on top of paper. So I don't know amount of the nanoparticle coated on the paper. So most of the time I would need to do TGA or ash content to measure, to do estimations, because the iron oxide nanoparticle stable at high temperature. Paper will be, I think, easily burnt and convert into ash. So the leftover residual representing the amount of the metallic oxide nanoparticle. But using furnace or TGA is time consuming, right? So long, you require long time. So should be a few hours, sometimes 6 hours, sometimes put it overnight. They say to convert everything into ash. So we use this, I use these FTIR instruments, then we measure we obtain the spectrum, okay, of the FTIR. So all background baseline corrected, okay, and also normalized, okay, normalized according to the one of the specific wave number, which is 1317, is the cellulose peak band. Then you normalize it. Then these are the spectrum that I managed to collect it. Then I noticed that the more the iron oxide coated on the paper, the greater the absorbance of all this peak representing paper, cellulose, hemicellulose, and some lignin. So these are the assignment of the functional group for paper. Then you may ask me, then why there's no iron oxide or metallic oxide peak? Yeah, metallic oxide, unfortunately, metallic oxide is not within this range. Metallic oxide normally below 500. So I did not manage to get that, but I tried to extract as much as possible information I have. Then I got this. Means then the higher the content of metallic oxide, the greater the lower, the higher the metallic oxide, the lower the signal, the lower the absorbance. So why? So I think it must be something to do with less absorbent, right? So means all of the peak, all the band actually reduce in terms of absorbent intensity. So means that the presence of metallic oxide on the surface of paper actually reduce the exposure of this functional group to the IR. So less exposure, less absorbent. So, and I do use multivariate software, principal component analysis, or to be more specific, partially square, PLS. Then we calibrate. We do a quantitative analysis. We calibrate it and found it turned out very nice. The regression coefficient up to 0.99%. So means that without using furnace or TGA, you can just spend few seconds, maybe 10 seconds or 15 seconds, just place the paper on top of this this crystal. Then you click. Then from the spectrum generated, you can estimate how much iron oxide content inside the sample. So this is one example. So happen to be that time the crystal is very big. It's a germanium one. Okay, it's very surface sensitive germanium crystal. Then the sample size, the paper specimens I have also very big. So then this is something I've done that time. Okay, so next one, let's go to the third one. Then before that, let me check whether any questions. No questions. If you have question, you can just stop me. So or else I will just continue. So next FTIR, next mode of FTIR is a reflectant infrared spectroscopy. So from the name, you know this is something to do with reflectance. It's not FTIR because FTIR is internal reflectance, but this reflectant is the detector measure the IR reflected from the sample. Okay. So these are the sample compartment that you normally use for this kind of measurement. Okay, there are three different types of reflectance infrared spectroscopy. Okay, so means that these three methods, okay, are all involving the measurement of reflectance of IR from your specimen. So incoming IR reflected, incoming IR also reflected. This one incoming IR diffuse, okay, refuse on the surface of your sample, then reflected. So means that this instrument, this mode, the detector will need to absorb all of the reflectance at IR at different angle. Okay, so you go one by one. So reflection absorption, so means sample IR beam come to your sample. Okay, your sample is on a substrate. This substrate can be gold. Okay, gold sample, because gold can reflect most of the infrared. So when IR beam come down, strike on the samples of sample, it pass through your sample one time, then reflected by the gold surface, passing through your sample another time, then detect by the detector. So means that your sample will have a chance to absorb 2 times the IR. So detector will tell you which wavelength or which wave number is missing or absorbed by your sample. Okay. Second, IR is directly reflected on the surface of your sample. So means that your sample must be reflective. For instance, like glass or maybe metallic. But this sample you need to do polishing, okay, to make sure that the surface is flat, okay, flat and reflective. So this is the first and second. Last one, diffuse reflectant. Okay, diffuse reflections, or we call it drifts. Okay, drifts spectroscopy. This is one of the most popular one, because the signal is very high. Okay, the spectrum produced is high in quality compared to the first two one. Okay, so IR is diffusely scattered on the sample surface. Okay, then the scattered light from into all angles will be collected by the instrument. So in the instrument, you have a lot of mirror. Okay, this mirror will reflect the light and send it to the detector. Okay, so this is drift. Advantages of drift is no sample preparations. All your sample should be in powder form. Then you mix with some KBR powder, because we know KBR powder has high refractive index. Okay, then it will increase the chance of the IR absorbed by your sample particles. Okay, no sample manipulation. You don't need to do any sample polishings. No need. Okay, can analyze non-transparent and highly absorbed material. So if you have dark sample, for instance, like carbon black or graphite sample, because you know dark color absorb IR, right? So that's why when you send sample dark sample in which is black color, you hardly get nice FTIR spectrum, because black color absorb IR. So most of the IR signal will be absorbed, then no transmitted. So in this case, if you have the excess of drips, okay, drips, then you can use it and to increase the signal to noise ratio. Okay, you can even do in situ measurement. So these are one example. This is one example. You have the compartment. You control the temperature. Then your powder is inside and your reactant is inside. You put in with some catalyst inside. Then you measure online in situ measurement. What kind of chemical reactions happen? What kind of functional group change according to time and temperature increment? So this is heating element. You have a furnace here. So you put the sample here, your catalyst here. Okay, then the IR light strike, then you measure. So this is in situ FTIR. Okay, very interesting and powerful tools for catalyst projects, okay, or experiment. Next one, FTIR microscope. Okay, so as I told you just now, I think I did mention to you just now, this instrument can give very interesting informations. Okay, because you can observe your specimen under microscope, then you can focus the laser, okay, the FTIR beam to one single spot okay, on the surface of your sample. So you are not measuring your whole sample, but you only measure one tiny spot. Okay, so it just like normal microscope. Okay, you have the lens, okay, objective lens. Then you have the camera up here, camera to take the image. Okay, then you have this objective lens. You have focus lens here. Inside here, you can change the magnification power. The sample holder, just like normal FTIR, a normal microscope. You can adjust the positions X and Y. Okay, then the only difference is you have one IR source and detector installed here. Okay, maybe here also. So it will lead the IR. Okay, this is from your the light source from the microscope. So it means that you have two optical paths. One is the light from the microscope, another one light from the IR source. Okay, both working at the same pathway. So this is just some schematic. So to show what is actually the principle behind. I will give you example later. Okay, about this FTIR microscope. So what are the applications, possible applications that you can use to collect FTIR spectrum using FTIR? One of the most popular industry or studies or research is on polymer, because polymer is organic material. They have carbon, hydrogen, oxygen, sulfur, nitrogen. So this kind of molecular bond or chemical bond is IR sensitive. Okay, so why MID-IR has chosen to detect organic functional group or chemical bond is mainly because organic chemical bond, the frequency is consistent with the IR wave frequency. So when you have same frequency, then there will be absorptions. Okay, so at least in the same range of the frequency. So these are examples of work that or spectrum that you can collect from polymer material. Polyethylene, mostly polyolefin like polyethylene, polypropylene, polystyrene. This is a very commercial polymer and very helpful FTIR. Very easy, simple, because polymer sample is very inert, very not sensitive to moisture. They are very inert and stable. They can easily obtain high quality FTIR spectrum from polymer sample. Okay, you can use transmittant or you can use ATR. The most straightforward one, you can use ATR, FTIR to get it. So the polymer sample can be in thin film. Okay, you can use transmittant or ATR. It is in fine powder. Even you can mix with KBR pellet, or you can directly press on the ATR crystals. Okay, or you put inside drift. Okay, if you have large item like rock or sand powder, then you can use drift. If a sample is irregular in shape, like a cylindrical, okay, or in the cube form, you cannot use transmittant because the sample compartment, sample holder has specific size. Then you can directly press on top of ATR crystal. Okay, if the polymer is soluble in solvent in the form of, let's say, chloroform, polystyrene in chloroform, or polystyrene in acetone, then maybe you can just mix in KBR pellet, or you can use ATR. Okay, if the sample is refractive, then you can use the specular refractant FTIR. If it is in single fiber form, let's say fiber, then you can use ATR. Okay, or IR microscope. So this is a table from Thermo Fisher. So it tells you what kind of polymer sample, in what form, in solid form, in layer, okay, in powder form, thin film form, okay, what are the possible mode of FTIR that you can use, and it gives you the rating also. So which one is excellent, which one is good, and which one is adequate. Okay, remember FTIR can be used for gas, liquid, and solid sample. Very versatile analysis. Okay. Example of microscope FTIR. Let's say I have a polymer film. This is from Bruker. They have a multi-layer polymer film, laminated, okay, in a thickness of around 75 micron. Okay, so they want to analyze. They say company B would like to know this product produced by company A. This product is very popular and very good, high quality. They would like to know, and they would like to produce another new product to compete with this company A. So they want to know what kind of polymer actually they are using, because from naked eyes, the film is transparent. You could not tell, actually hardly tell what kind of polymer they are using to laminate and produce this film. So one possible method, you use FTIR microscope. You cut a sample, you take the cross sections of it, okay, the cross section of it, then you point the laser, the IR under microscope, and you can program it. Then the instrument will scan across this whole layer. Okay, so this is from the cross section of the film. So you put in the command. Okay, you just drag this area, then ask the instrument to scan every pixel. Okay, the pixel is few micron. Okay, the size of pixel is few micron. Then every micron of the pixel generate one FTIR spectrum. Then you can imagine, they say the scanning is from here. Then when it scan the first layer, then the computer will record the FTIR spectrum. Next one, next one, next one, next one, next one, then go to another layer. So you have another types of spectrum. So when completed, you have one FTIR image that you can tell the software, okay, let's say I know this is polypropylene, they say this is polyethylene, for example. Then okay, please label polyethylene functional group with green color, polypropylene with red color. Then you have one FTIR image. Okay, this is one very powerful functions of FTIR microscope. So means that you no longer take FTIR spectrum from one bulk material, because always remember, when you have this kind of spectrum, you're just telling me that your material contain this. But in microscopic level, you may have impurities and also other types of chemical or materials. So whatever mode of FTIR I explained to you just now, besides except the microscope FTIR, they are for bulk sample. But if you have micro sample or sample with micro size or millimeter size of distribution of different material, then you can use FTIR microscope. Okay, so again, this is powerful for polymer because polymer is sensitive to mid-IR region. Okay, not only Bruker as the instrument, there are company also, many companies, they have the same instrument for FTIR microscope. So with this, even better, you can measure the thickness. Okay, you can measure the thickness of the polymer film, the laminates. So this is normally done by competitor when they would like to reverse engineer, okay, certain product in the market. Or you can do quality control. Let's say you have customer claim. Let's say you produce this film and sell to a customer, and customer tell you that the performance, the strength of the film is not as claimed, as promised during when they place the order. So you can do some investigation like forensic study. You can know what is that. That is wax, or that is blood, okay, or that is human skin protein, okay, is also possible. Okay, so I show you one study we have done recently before I stop for break, another 20 minutes. Okay, so this is a study we conducted in 2019. Okay, published this in 2021, and takes time because of pandemic. So we receive a funding, okay, from industry to produce some kind of adsorbent material for wastewater treatment, and the targeted wastewater is ionic dye, okay, which is negative charge, okay, negative charge dye, and also heavy metal. So we use chidosan because chidosan is a very, how to say, is a very common material, very cheap, abundantly available, can be extracted from streams, from crab. So this is easily available, so you can buy at very low cost. So we produce a method, a protocol to convert chidosan into bits, a small bits form that is highly porous, and it contains some chemicals, polymer here, cationic polyethylene imine, which is a cationic in charge, high molecular weight, so that a lot of functional group that can absorb, interact with the negative charge compound, heavy metal, and also dye compound. So these are some introduction of it. So wastewater, okay, a lot of dye, heavy metal, but you have positive compound, positive charge compound, and also negatively charged compound. So you need two things, actually two types of adsorbent. One is positive, and one is negative. So in this project, we produce cationic adsorbent from chidosan. So common method normally people use is coagulations, okay, coagulation. But in large volume, coagulation is very costly because you are adding in the coagulant, and the coagulant is also expensive, okay, to treat large volume of wastewater. So we design the bits so that it can actually so it can take, then we can recycle it, can reuse it. Okay, that's the whole purpose of it. So this is PI, polyethylene imine. Then you have a lot of amine group, okay, high branch, high molecular weight. So a lot of high positive charge of functional group for taking the anionic compound. So this is chidosan. I'll just skip. So yep, this is the. I'm not sure whether this video is working. No, it's not working. Yep. Oh, the video is not working. It's fine. So this is a chidosan solution in acetic acid solutions, then with PAI inside, and this bath is in this vial there is sodium hydroxide alkaline. So chidosan dissolved in acetic acid solution, and we mix with PAI, the polyethylene imine, the positive charge polyelectrolyte polymer. So when acetic acid meet sodium hydroxide, neutralization will happen. So chidosan will convert from liquid form, dissolved form, into solid. So because of the geometry of the droplets, then the bits is in spherical shape. So during the regenerations of chidosan from liquid to solid, it will also trap the PI, the polyethylene imine, inside the bits. So it's something like a egg and with some ingredient inside. Okay, so and we wash it, then we use these bits, okay, as the adsorbent material to remove the negative charge compound. Okay, so and we check the morphology of it, and it's highly porous. Okay, it's highly porous. They measure the surface of it, okay, the surface area. And okay, this is the key results I want to explain. And we would like to know, since we have the bits, okay, the bits is in around 3 mm size of diameter. We'd like to know where is the PI located in the bit. So this is a bit. After we freeze dry it, the shape become a bit irregular, no longer so spherical, but still fine. Then we cut the bits into two. Then we send it to FTIR microscope. Then we also analyze control chitosan polymer, this dark color spectrum. Then we run the PI. This is PI amine. You see the amine is very intense, the peak. Then another amine is here. So, and we also check the chitosan bits. This is chitosan bit, sorry. This is gray color one, chitosan polymer, the standard sample. This is chitosan bits. Okay, and this is chitosan bits with the PI inside, 30% of it. So you can see when you have, I think good thing about this study is the chitosan, the raw chitosan and the raw PI has different spectrum. You see the gray color one, chitosan, and the PI have this amine and has this amine group, which is not, and also this CH group, which is not presented in the chitosan raw chitosan. So we ask, the instrument actually run the mapping, okay, of this cross section of the bits, and we collect thousands of spectrum over this cross section area, and we tell the computer that please plot chitosan peak, okay, chitosan peak, okay, let's say what peak chitosan has but not presented in the PI in green color, okay, and the adsorbent bands for amine, okay, amine or the PI in red color, okay, in red color. So eventually this is the result for the chitosan without PI. You can see most of it is chitosan, so it's quite homogeneous. Then for the chitosan bits with the PI, we have chitosan on the surface mostly, inside very minimal of chitosan. Then for PI, mostly trapped inside the chitosan bits. So this FTIR image tells us that the encapsulations of the chitosan, of the PI by chitosan during the regeneration process has successfully entrapped most of the PI inside the chitosan shell. So this kind of image is impossible for you to obtain from any characterizations, any instrument. For instance, like even optical microscope, you cannot tell you the chemical functional group. SCM also you cannot tell. So the only thing you can do FTIR mapping, or even maybe Raman mapping also. Okay, it will cover, actually I'll cover this in the coming lectures later. Okay, so by using this, then you can convert optical image into chemical image. Okay, so optical means visible light image, but this one is infrared image. Okay, so you can do comparison, then you know what chemical, what functional group, or what chemical bond, okay, is inside a sample, and from the chemical bond you can identify what is the material. Okay, so this is one of the example of how we use FTIR microscope, okay, for sample analysis. And eventually we use the bits to absorb the dye. So the performance we found that the performance is not too bad, it's not very good, but at least it's usable, and it can be recycled. I think this is the important part. So as I told you just now, if you use coagulant in big volume of wastewater, you throw it inside, then it will coagulate all of the material. Then eventually you cannot trace it back. You cannot collect it back and reuse it. But just by encapsulate it in certain kind of polymer, in this case it's chitosan, then you can recollect it, then you can regenerate it using, let's say, in this case, you can use sodium hydroxide to push away the ionic compound, then you can reuse it. We reuse it up to 8 cycles, and we found that the performance is still retained. Okay, it's still retained even up to 8 cycles. Okay, so this is one of the example. Okay, so that is for FTIR microscope. So I think should we stop for lunch? Because I'm entering a new topic, or any questions? Any questions from the participant or students, if you have? Mr. Saria? I mean, Mr. Saria is not around. I think maybe I can continue for another 5 to 10 minutes if you. Okay. Yep. So okay, I explain. I continue maybe for a while, 5 to 10 minutes. Just now I give you example of applications of FTIR for polymer. Okay, using transmitted FTIR using ATR. Then I give example about FTIR microscope for also polymer study. So, and we have to remember FTIR is also very good for carbon-based material. Okay, it's also a very good good instrument for carbon-based material like diamond, okay, graphite, okay, graphene, because in all these carbon-based material, you have carbon, oxygen, okay, hydrogen functional group. So this is IR sensitive, okay, IR sensitive material. So one of the example of application of FTIR is to differentiate fake diamond and real diamond. Okay, fake diamond, for instance, like zirconia, okay, zirconia, and monzonite, okay, monzonite is also fake diamond. Monzonite is silicon carbide, okay, silicon carbide. So most of the fake diamond in the market can be either silicon carbide or cubic zirconia. Then the price differs a lot, okay, differs a lot. So one of the most widely used method or instrument, okay, tools to check diamond, real or fake, is using thermal conductivity. So there's a instrument, we call it thermal pan test. So as we know, diamond is a very good thermal conductor. Okay, it can conduct heat very nice. Okay, excellent. So silicon carbide and also zirconia is low in thermal conductivity, but the thing is, because diamond is naturally occur material, so it's from the mineral, it's a mineral material, so it contains impurities and also some imperfections. So this kind of impurities and imperfections will affect the thermal conductivity. So some authentic real diamond may have low conductivity because of the impurities. So if you use thermal pan test, it will lead you to wrong decisions. Okay, so and another method is actually examined by human. So germanologists, okay, they'll have the experience to check the quality and also the authenticity of diamond. So but this is very costly and human, and the time that is very time consuming. Okay, so diamond has been also analyzed or characterized using FTIR. Okay, just show you the spectra of these 3 different material: diamond, okay, because of a lot of carbon, hydrogen. Okay, so you have basically a very wide range of spectrum, okay, absorbent band. Then for another two, because they are not organic material, zirconium oxide is mineral is from transition metal. It's not carbon based. Monzonite, silicon carbide, is also not organic material. So the spectrum is completely different. Okay, so what are the advantage here is first, very quick measurement. Okay, within second, you can immediately get the spectrum. You can tell you what is what, and very low error because the sensitivity is good. Because this is there will be no misjudgment, because if you have carbon, hydrogen, carbon peak, carbon band, it will give you the signal. For another two, silicon carbide and zirconia, this will be the spectrum. Okay, this is one example of it. So one of the most important absorbent band is 1332, which is the asymmetry stretching of the sp3 carbon-carbon bond. Okay, so means that you can use very straightforward and also simple method, very quick result, quick method to do some for analyze a very expensive material, which is diamond. Okay, so these are the crystal structures of zirconia, diamond, and also the monzonite. So FTIR would not tell you the arrangement of atom. Okay, bear in mind, FTIR actually even down, which it give you the vibrations. Okay, information about the vibrations frequency of chemical bond. To know the crystal structure, you need XRD. Okay, because diffractions. Okay, diffractions will tells you the crystal informations of the material. So if you want to collect more information about materials, then you need to include different types of characterizations instruments, analysis instrument, analytical instruments. Like in this case, you use FTIR to extract chemical vibration frequency information in the sample. Okay, so it's actually between atom and atom. But for arrangement of crystal, okay, you need to use XRD. So if you want to know optic, like band gap, okay, then you need to use UV, okay, UV visible spectrophotometer. Okay, so different instruments serve for different purposes, but most of the time you can combine everything into one, then to make more comprehensive discussions. Okay. Okay,
Prof, excuse me,
yes.
Prof.
Yes,
Prof, we are already arrived at our lunch break time. So after lunch break, we have only 30 minutes. Is it okay, Prof?
Yes, no problem.
Okay, Prof. So we'll back exact 1 p.m. and 2 p.m. in Malaysian time, and our session will be finished 1:30.
Yep.
Maybe 1:25 is okay.
Yes, sure. No problem. Yes, thank you.
Okay, thank you, Prof.
Thank you. See you later. See you around later.
Good afternoon, Prof.
Yes, good afternoon, Mr. Sarah.
Yes, Prof. I think you can start earlier, and
Yes.
we can finish 1 to 5.
Yep, sure.
Yeah.
Thank you.
Okay, Prof.
So I share my button. Okay, so we continue. So thanks for
Yes,
joining
Prof.
back. Yep. So just now I give you examples, an example about diamond. So and I told you that FTIR is a sensitive instrument or analysis method for carbon-based material because of the carbon-carbon bond, carbon oxygen bond, carbon hydrogen bond. So next one, I will share with you one study. I think I used this example in many, I think my previous talk for XRD. And so this is about productions of graphene oxide from graphite. So the method we use is to use strong acid, sulfuric acid, phosphoric acid, and also strong oxidizing agent, which is a potassium permanganate, to introduce oxygen functional group on the layer inside the graphite flakes. So the stacking of graphene in graphite has to be loosened up before you exfoliate it into single layer of graphene or graphene oxide. So we use the same chemical, but we study the oxidation time. So functional group introduced such as carbonyl group, carboxylic group, epoxide group, hydroxyl group will be the functional group that loosen up, expand the graphene layer inside the graphite. So we use FTIR again. My previous topic, we talk about I talk about this XRD. We use XRD to see the inter lattice spacing, the D spacing in the graphene layer, okay, of the graphite flakes. So the shift of 2 theta to lower 2 degree representing the exfoliations of the layer of the graphene in the graphite flakes. So this result has to be supported with FTIR and also Raman, because XRD tells you the structure of graphite flakes has been loosened because of the oxidation. So we need to prove that they are oxygenated functional group introduced onto the graphite flakes. So the first one is the graphite flakes, you see. So I told you just now, FTIR is not really good for measuring dark color sample, especially for those functional group or chemical bond which is not really polar, okay, with low dipole moment. So the signal is very poor actually if you look at the top one. But quite fortunately, over the oxidation process, because of the introductions of new functional group like this one, so these are the chemical we use. So because of the introductions of this chemical acid and oxidants, new functional group will be oxygen functional group will be introduced onto the 2 layer of graphene, the graphite. So such as carboxylic group, okay, carbonyl group, hydroxyl group, okay, and also epoxide group, you can see. So all these functional group appear inside the FTIR spectra obtained over the increment of the oxidation process up to 24 hours. The intensity is not really directly proportional to the time. We suspect this could be due to inconsistent. We may not have a homogeneous mixture during the oxidation. The one we collect, the specimen that we collect at different time may not really represent that time, but we can see overall the intensity actually increased, okay, overall, but not linearly increased. But what we want to do prove here is the success of introductions of the functional group So which can be proven by the FTIR spectrum. Okay, this is important. So to support here, what we have claimed from the XRD result, further supported by FTIR. So I think this is something that very important and could useful to support the discussions. So and to convince reviewer and or the readers about your discussions. Okay, so it has to be supported by, if you can, more supporting results, the better. Okay, the more the better. So the functional group can be assigned a certain wave number. So this is, I think, quite consistent with the database and also previous publication work. So from this work, I think the students just refer to previous publications, okay, then follow the wave number and plotted using the Origin Pro, then label it accordingly. So this kind of labeling can be done using Origin, okay, Origin Pro software. So just follow something like this. I think it should be clear enough, the informations. So if you want, one suggestion is if you still remember, you have the fingerprint region. Okay, this fingerprint region can be magnified and enlarge it so that you can see clearer. Okay, where is the band that you are mentioning? Okay, that's an important point. Okay, so yeah, it's supported by XP, this Raman also. So this will be included in my next topic. Okay. So all this image just claims that they are oxidations and the structures gets loosened up. The graphite flakes expand because of the oxidation happen. So it gives stable graphene oxide suspensions, and the TM and AFM confirm the thin layer of graphene oxide produced from this study. Okay, so this is another example for carbon-based material using FTIR. Okay, next example. Next 2 or 3 example I will give you. I would like to introduce here is on compositions estimations and also quantitative analysis using FTIR. So like Mr. Shahriar has experience in ICP MS to measure concentration of metallic compound or maybe some organic compound using HPLC, UCMS. Those instruments are very advanced instruments and very accurate, okay, accurate and with high performance and very high reproducibility. But those instruments are also very expensive, and then also the cost of maintaining is also very high, and most of those instruments require tedious sample preparations. For example, like you need to filter it, you need to do acid digestions, you need to remove impurities, so you need to purify the sample, which without doing that, you may introduce background or noise to the signal. So pros and cons. So then there are various examples of studies actually conducted and also reported. If you just type keyword quantitative analysis, FTIR, compositions estimation, you will find heaps of publications of work, and some very interesting actually. So I give you a couple examples here, and I will explain a bit, not so detailed, but at least I give you some idea. The standard procedure, okay, how to conduct this kind of studies, okay, using FTIR, and how to do the multivariate, the statistical tools that you can use to prepare calibration curve and to verify that the calibration curve that you prepare is accurate and low in terms of error or the deviations. So I will give you a couple examples here. So the first one is using ATR FTIR, okay, using FTIR to estimate caffeine in soft drink Okay, so this is tea and tea and coffee and also some other drinks contain caffeine. So caffeine is one very interesting compound. Some say is good for our body. Some say if you overdose, if you overconsume, it may encounter some side effect. So that's why to quantify the compositions or the content of caffeine in food and drink is always a very interesting study. Okay, people can try to relate uh, the effects of this kind of drink to our health. Okay, so this study used ATR. Yeah. Okay. Then they produce a spectrum. Okay. Then they do spectra treatment. What I would like to want you to pay attention is the spectra treatment. So spectra treatment here is basically what I explained to you just now. Baseline corrections, smoothing. Okay. And if you think that normalizing your spectrum is something useful to produce good data, I think normalization or normalizing of your spectra is something you can consider. So all these spectrum or spectra treatments can be carried out using Origin Pro. Okay, so I did not include the video here, but you can just use keyword. Okay, Origin Pro, then normalizations. Okay, normalization or multivariate calibrations using Origin Pro. All these steps can be conducted using Origin Pro. So Origin Pro is a very powerful tool for you to collect to process the spectrum. Okay, do treatments on it, then to do quantitative analysis. Okay, so all can be done using Origin Pro. And then eventually, the calibration method has to be verified using unknown sample. So you need to prepare some couple of sample for you to verify it without knowing the real concentration. Then you can prove that the model that you develop, the method that you develop is correct. So this is the ATR spectrum of caffeine. So you see, this is caffeine molecular structures with methyl, CH3, C double bond, C. Okay, then you have C double bond N, C double bond N. Okay, C double bond O. This is a carbonyl group. So all can be clearly assigned. Okay, can be visible in the spectrum. So the quantitative analysis method that you develop using the multivariate analysis is based on the range. Okay, the range of wave number that you know that they are absorbent peak. Okay, absorbent band in that range. Okay, for specific functional group. So you consider the whole range of it, not consider single peak, because always remember this peak 1218 can be also from other compound presented in your material, in the drinks, right? So you cannot just only rely on one. It has to become in a package. So the multivariate, the partial least square, or the principal component analysis software that you develop or you use and develop the method has to consider the range of spectrum, okay, the range of wavelength, okay, which contain specific functional group of that particular compound. So you may not necessarily take the whole range, but you can split it into fingerprint region. Then another region here, let's say this, you think that this is very important, then you can try to see whether by combining this region with the fingerprint region, can you get better regression? Okay, regression. So that is how you develop the method. Okay, so the developed method using a partially square model. So this is under one of the function under principal component analysis. Okay, so they study the region. Okay, different region from 600 to 1000. The R square is pretty low, so it means that from 600 to 1000 is around, okay, below here. So this, I think the range cover is very low. The number of band of the possible functional group is very low. That's why the value is very low. So the spectral region extend, I think at this 1,000 to 1,500. Yeah, this is high. It's getting higher. Then 1,500 to 1,800 is also high. So if you notice here, from 1,000 to 1,800, this is the fingerprint region for carbon, oxygen, and hydrogen chemical bond. So that's why the radiation coefficient is very high. Okay, so they also study two region. Okay, 1,000 to 1,500, 1,500 to 1,800. So two region also give you kind of high R-square value, radiation coefficient value. So also 1,500 to 1,800 and 2,800 to 3,000. So where is the region that you, spectral region that you choose is really depends on the R-square value. And 0.992, 0.98, 0.98, 993, 0.986 is something I don't think it is significantly different. Okay, it's just fall in between the standard deviations of the R-square obtained. So what does it mean? Means you can always choose, as long as you are comfortable or you're confident with the R-square value, that could be the method that you develop. So what does it mean? Means that when you develop a method, okay, a model using partial least square, I think in origin pro, you have this function, then you can calibrate, you can run, you can collect FTIR spectrum from caffeine model compound, okay, at different concentrations. Then you need to collect the concentration over, this is the caffeine concentration here, you collect it, okay, collect, then using the model you develop, you plot the estimated concentration of the, this is the real one, okay, so you can plot it, this is the real one, okay, this is real one, because this study, they use UV method to measure the caffeine content. Then this is FTIR, okay, so they assume that this is an accurate method, okay, and can be replaced also using FTIR. So they use UV as a method to measure the caffeine concentration and compare with the caffeine concentration estimated by FTIR using this kind of this spectral regions. Okay, then I think they choose only one from here, then they plot it. Then FTIR versus UV. So you can see the linearity is not so bad, actually 0.95. So means what? Means you can either use UV or UVs or FTIR as a tools to estimate caffeine content in drinks or food. Okay, so this is an example. So how they prepare the sample for the FTIR, they'll dissolve. Okay, they'll use the chloroform to extract the caffeine compound from the drinks, so that they have the mixture or the analyte sample with only caffeine before they do the measurement. Okay, so next one, I think before I go to, okay, I think I can just go quick one. Besides carbon material, polymer, beside natural compound, FTIR is also very useful for geochemical research, like geology sample, rock, soil, sand, because all these kind of sample contain various types of compound, and many of these compounds is also sensitive to IR. So why FTIR is potential or also has been used in this area is because the existing method, for example, AS, ICP, okay, ICP-MS or ICP-OES, this technique requires sample preparations. Okay, you need to hydrolyze the soil sample, the rock sample using acid and put into microwave digester, and dissolve the hydrolyze the metal. Then only you measure the metal concentration and you back calculate and predict what is the compound that you have. So that is quite quite tedious in terms of the steps and also time consuming. Another one is all these instruments are very expensive and high cost in terms of maintenance. So AAS using gas, okay, ethylene gas. Then this using argon gas is also very expensive. So, and also the time taken to run the experiment is very long, much longer compared to FTIR. Okay, so compound that can be detected using FTIR for geochemical sample as such. Okay, I think I will go to the last one. So I just give you another example. So I think everyone know about amphetamine and also methamphetamine. So this is drug, okay, ecstasy. This is a banned, actually prohibited, and quite common misused by many people. So to detect it, normally we use titrometry, okay, titrometry using titrations, capillary electrophoresis, or advanced instruments like HPLC DAD, okay, or GCMS, okay, powerful GCMS to measure the concentration of it or to detect the presence of this compound. So these instruments all are very sophisticated, okay, and normally require skilled worker to do all the calibration, to conduct the sample preparations, to interpret the data, to interpret the chromatogram, to interpret the MS spectrum. That is very tedious, okay, and sample preparation also, you need to dissolve it, you need to purify it, you need to filter it before inject into HPLC or GCMS. So that is also expensive. And last but not least, the time taken will be very, very long and relatively longer compared to just drop on the ATR diamond, ATR and FTIR. Okay, so this is the structures of the methamphetamine. So amine, methyl, and one benzene, very simple structures. So this study developed analytical method, okay, developed checking method to quantify methamphetamine using ATR, FTIR. So this is the structures of it, okay. You have the amine, NH here, amine is here, 1603. Then you have the double bond, C double bond C, or in aromatic, 1486. So if you notice 1486, you know that they are C double bond C in aromatic form, okay. Then and also methyl, okay, CH2CH in aromatic ring. So these are the functional group appear in the compound. So with this database, with this spectrum, you can develop the calibration, okay, calibration line. Then to do the calibration using multivariate, either principal component analysis or partially square. Then to choose the right, okay, the right region of calibrations using known concentration sample, okay. Then you use you select the best linearity, okay, in terms of regression coefficients. Then you validate using unknown sample to prove that it is correct, accurate. Then that model can be used for real applications. Okay, so I give you an example. In Canada, the government even provides free checking, okay, free testing for any one of the citizen that would like to. They have some sample. They want to check whether the sample is contaminated by drugs. So they have stations everywhere. Okay, a lot of places. They click in, then they'll provide the locations for you to bring the sample. Then they'll run the analysis for you. Okay, and very quick one, just 10 minutes. Okay, the test take about 10 minutes from start to finish. So if you have something like heroin, cocaine, methamphetamine, okay, all these fentanyl, all these the dangerous drug, you want to check whether it is these types of drug, or you want to check the contaminations, okay, the concentration, you can just drop by, okay, and they will run the test for you. And they even mentioned it, they run it using FTIR. Okay, Fourier transform FTIR. So this is a very common method already in the world, and many possibility for you to do. And you can tailor, okay, you can tailor make one testing method for compound that you are interested in. So for instance, like you are doing natural products extracted from, let's say, from plants or from animals, okay, then you can use FTIR. Okay, FTIR, they develop a testing model, okay, a quantification model, then you can do fitting, again, then immediately you can use that for your upcoming sample. And very quick checking method, just few seconds, few minutes, you can get the data. Okay, you just get the spectrum, fit into the calibration curve, then you know the concentration. Okay, so okay, this is another example, biomedical research. So I just want to show you, not only geochemical, not only carbon, not only polymer, biomedical, like FTIR is also sensitive to DNA, okay, sugars, okay, biological compound like our bodies, okay, cell, protein, is also possible. Okay, so just throw some idea to you. So if you happen to be fit your research, then you can think about it. Okay, so I think that's all from me. Thank you very much. Thank you for attention. Yep. Hi, Mrs. Sarah. I think
Thank you, Prof. Thank you so much for your session. So I think you have another business. So today
yes.
and also our student, they doesn't have too much questions. So maybe we can finish our session here, and our next session will be next month. It will be our final session. So
Yep.
maybe that day I will give you the maybe we can summarize our this semester session, and 4 hours, maybe we can divide it by 2 hours and 2 hours for discussion with overall our semester.
Yep, that's a good idea. So that I don't need to talk so long, right? So you have questions.
That day because of it, this is although it's the project of our university, so because of as a teacher we are supporting 4 hours just as a academic support. So in that case, we will bring our student to sum up the seminar class session, and that day 2 hours, last 2 hours, maybe we can discuss about this, the whole seminar. If they have any questions, they can directly ask you.
Yep,
and 2 hours we will just technical part.
Yep, that's a good idea. Thank you. I will do that. So I will prepare the lecture for 2 hours.
Yes, Prof. And I will let you know, Prof. Thank you so much, Prof.
Thank you very much, Mr. Sarah, and thank you for all the attention given by the student and also the staff, if there is. So I hope to see you again.
Yes. Okay, Prof. See you.
Thank
Prof.
you.
Thanks.
Thank you. See you. Bye-bye.
Bye-bye. Thank you so much, all of you.